Alright, so what we're going to do today is finish off our bootstrap process, and you'll see how ugly it is, and then we'll talk about the solution that people are starting to adopt. And it's pretty widely used now. At some point I'm going to have to redo the second assignment, and I don't know, hopefully not Pintos, we'll have to see, but to start using UEFI. And I'm not excited about that, but hopefully it won't be too horrid. But we had started talking about bootstrapping and this whole issue that we have a machine that requires a program to know what to do, but it doesn't have one when it starts. And so there's a process by which we get to the point that it's actually executing our program. And so, like I say here, it's a series of increasingly complex bootloaders. Each stage takes a step forward, it loads the next stage, and then off we go. And so we start out with a very simple step of saying, hey, here's 16 bytes, do what you will with it, and typically it's jumped to something more complicated, and that loads in something more complicated, and blah, blah, blah. We go down this process. Okay, and we started covering the IA32 Bootstrap process, and like I say, the details were grungy so far, but they get worse. And the real reason why is because we have to maintain backwards compatibility. Do we really? Well, yes, there's a few people who still try running DOS on their computers. You know, they're fancy advanced systems. I might have tried it once or twice. So, you know, you still have to maintain backward compatibility so these old pieces of software don't get confused. They know what to do. So IA32 has segmented memory. That is the general approach of the IA32 processor instruction set architecture. We're going to talk about that a lot more when we get into virtual memory. So just for now, why? Well, it's just the way it's designed, and we'll talk about more of the reasons when we get there. And there's multiple addressing modes. We start off in real addressing mode. Remember, we have a segment value and an offset value, and the segment, it's called a segment selector, but it's a 16-bit value, and it's actually used to compute the address. So we shift it left by 4 bits, or we multiply it by 16, and then we add in the offset, and that gives us our address that actually goes to memory. So that gives us our physical address. Protected mode is much cooler, and it's much more configurable, and so we have this thing called the global descriptor table, which we can use to specify the details of each segment. Where does it start in physical memory? How large is it in physical memory? What are the protections for it? And so all of these things are used to translate addresses in this way. So you take the segment selector, look up in the global descriptor table. Okay, what's its segment descriptor? You pull out the base address, you add the offset to it, and that gives you a linear address. So that's good. That's part of the process. What we do then, so just to touch on what operating systems generally do with this model, you can do a lot with it, but OSs generally just set it up to be simple. The base address is 0. The size is the entire address space. And so this mapping is basically just a one-to-one mapping. The offset or effective address just gets translated straight down, add 0 to it, who cares, we come to a linear address. So this mapping part is simple. Okay? But there's a giant part of it that I'm leaving out right now because we're not talking about virtual memory. That little map to physical address thing in the bottom right corner is the virtual memory system. So this is where the page table, page directory, base register, all of that stuff fits in there, and we use that to map the linear address to a physical address. Okay. But what's really cool is we can just turn that part off too. So if we want to do that, then the linear address is our physical address. We don't do any mapping. But most operating systems, they don't use the global descriptor table to do their process isolation, although they could. Instead, they use the virtual memory system to do their process isolation. Okay? So that's just the overview of this stuff. Okay, so we talked about starting up at address, lots of F's and then a 0. And we do the power on self-test. We talked about all of this stuff. The only interesting details are the boot sector is loaded by BIOS into a specific address, 7C100. And we have 512 bytes to do our thing. Really, we only have 510 bytes. But really, we only have like 430 bytes if we're a real operating system. So, and if it's a master boot record, then we need to go ahead and chain load the next boot sector that's selected. Okay? And so that we sort of fake this process for whoever comes next if we need to chain load. Okay? So finally we get to a bootloader that's the operating system's bootloader, and that's the thing that gets to start setting up for the operating system. So that's what we're going to talk about today. Okay, it loads the OS kernel somewhere into memory, and then it jumps to the kernel bootstrap code, and that startup code sets up the hardware so that the operating system kernel can actually do its thing. Part of this is to transition into protected mode, which is exciting and scary at the same time, because in one way you are opening up all the facilities that the hardware has to offer, but on the other hand, you no longer have BIOS to take care of things for you. Now you have to start doing things yourself. Okay? There are other annoyances that you run into on IA32 or x86 systems. So the first thing I mentioned briefly before is that you have a 1 megabyte, or technically it's a 1 megabyte, but I hate saying that because it sounds silly. It sounds like you're making up words. But you have 1 binary megabyte of address space. So you have, 20 address lines, A0 through A19. But if you look at real addressing mode, you realize, hey, I actually could access past that 1 megabyte address range. Okay, so for example, if you do this FFFFFFF, then you can end up going a little bit under 64K past that 1 megabyte barrier. Okay, so if you have a system with 4 megabytes, then that's actually some space that you'd like to be able to utilize. So you start wanting to expand your address space. But the original 86 had only 20 address lines, like I was saying, A0 through A19. So anything beyond that, if you think about what would happen if you tried to execute past the end of this, you would just wrap around. And unfortunately, there were programs that relied on this, typically BIOSes that were in that space. And so they start executing, they fall off the end of the address space, but thankfully the world is round, so they end up on the other side, coming around the other way. Why would a program ever do this? I don't know. Does anybody do this now? I sure hope not. They should be beaten if they do. But so BIOS needs to support this. We need to be backward compatible, so we disable the 820 address line if there is one. Ugh. So that we can retain only that 1 megabyte address space and this really bizarre behavior that some weird, stupid programs actually depended on. So 820 address line is disabled. It's forced to 0 at startup. If I want to access more memory than 1 megabyte, then I have to re-enable that 820 address line. Yes, every operating system has to think about this. If you're like, seriously, you can't be serious. Every operating system has to think about this kind of thing. Okay, so yeah, like I was saying, for backward compatibility, the 820 address line is typically left disabled at startup time, and so it has to be re-enabled. Sometimes it's taken care of by BIOSes, because a lot of people say now, wow, that's a really dumb constraint, and so the BIOS will take care of it. Bootloaders like Grub take care of it for you. So Grub, for example, sets up the hardware in a specific way so that operating systems can just know that it's all good. So thank you, Grub, except now you've actually made operating systems a little bit more complicated, because now they have to check if it's disabled and then re-enable it if it's disabled. But if it's already been enabled, then they shouldn't do anything. And so that's another thing they have to think of. Instead of just always re-enabling it, now they have to check as well. So whatever. Thank you, Grub. That kind of sort of made life a little bit different. Okay. So the other step. Startup code has to configure protected mode and then switch into it. And like I said, you also have to enable virtual memory. Most operating systems use virtual memory, so that's something else that you have to set up. Like I said, you have to at least set up 2 segment descriptors, one for code and one for data. Because remember, there's CS and there's DS, and the processor automatically uses various segments when it does things. So you have to make sure that you have a code segment for the code so that when it loads instructions, it always automatically uses the code segment. You have to have a data segment so that moves will automatically do the right thing. Obviously, if you'd like to use a stack, then you should set up the stack segment as well. Okay? And if you're doing virtual memory, then you need to set up a page table as well. I'm not going to spend very much time talking about that. There's some really interesting and clever things you have to do in your startup code, because typically one of the things that happens is the kernel is loaded below 1 megabyte, but then you need to move it above 1 megabyte. In fact, you move it above 3 gigs if you're on a 32-bit address space. Well, how do you do that? Well, you just configure the virtual page table mapping so that the kernel appears in 2 places. and then the low part jumps to the high part, and then voila, you're where you're supposed to be. So the kernel has to think about these things. Thankfully, we don't have to talk about it right now. Okay, so we switch from real mode to protected mode. And again, more complicated than you think. The work you guys have to do on the second project is like the simplest possible version of it. Okay, so there's a few details even omitted from what I'm going to give you, and it's like an eight-step process here. So you disable interrupts, and the IA32 manual is really explicit about this. They say if any interrupt occurs at all in this process, the world will end as far as the processor is concerned. It's like, you know, all hell breaks loose. They even say if it's possible to disable non-maskable interrupts in hardware, disable non-maskable interrupts. That's how serious the manual is about. You've got to disable interrupts. Next thing you do, you set up your global descriptor table, because remember, this is how protected mode figures out where addresses should go in physical memory. So we have to set up that mapping. And again, it's really straightforward. The booter that I give you, the global descriptor table is stuffed into the boot sector. That's not normally how you would do it, but it's small enough. It's like 16 bytes or 24 bytes. Just cram it in there and just point to it with the global descriptor table register, and that's all you have to do. Third thing, and this is something we don't do in our booter, but operating systems have to do this because remember, they have multiple protection levels that they run code in. Our booter is all in ring 3 or ring 0, so it's like we can do anything we want, which is probably dumb, but it's the way we do it. Operating systems start out in ring 0, but then they also want to run code in ring 3, and when you transition between the two, you switch stacks. The task register says how to switch stacks. That's why we don't have to do it, because we never switch stacks. But if you're going to have user space and kernel space, then and user mode and kernel mode used in your operating system, you have to have the task register set up. Finally, you get to turn on protected mode. Yay! That's it, right? No, there's more steps after that. But you'll notice that you write to control register CR0. It's full of bits that enable and disable various things. One thing that's kind of interesting, I'll just mention this as an aside. I don't know if any of you are going to try to use floating point in your booter. If you do, be forewarned, there may be icebergs that you run into because, you know, well, there is a coprocessor on all of our modern IA32 processors, so that's not a problem. And we're not doing context switching, so you don't have to worry about saving floating point registers and so forth. So I think you'll probably be okay. It should be fun. See what happens. So if you try that and you have success, let me know. I might even give you a couple of bonus points for that, because that would be a cool thing to know. Anyway, there's some details in CR0 you can configure as far as coprocessors are concerned. Okay, and of course, if you turn on paging, then you also need to set CR3, which is the page table base register, or the page directory base register, so that you can actually have a page table. Okay, so we're all done, right? Well, the only issue is the processor is still running in a 16-bit real mode code segment, because that's cached inside the processor. So even though it's in protected mode, it's still using all that real addressing stuff. So we need to change the code segment to the new code segment we just set up in the global descriptor table. The way that we do that is by doing a long jump, because a long jump specifies the segment selector as well as the offset to jump to. Okay? So what do? Well, we just say, use this code segment now. Where do we jump to? The very next instruction. Okay? Simple enough. You'll see exactly how to do that in the booter, because this is part you do not have to do. Okay? It's mechanical, so why make you guys do it? Okay? So anyway, you do a long jump to the next instruction that forces CS to be reloaded, and obviously you go from using IP to EIP, because now you're in 32 bits, and off you go. So you're pretty close now. Next thing you have to do is set up your other segment registers, which again I think I do for you. I can't remember, but you have this data segment you set up. So you set DS and SS and ES and FS and GS if you want to use those. You point them all to the data segment selector you set up. And now you're basically all set. If you want to handle interrupts, which again all operating systems do because polling is dumb, then you set up the interrupt descriptor table register. Okay? It turns out that you could actually build all of the facilities you have to build in the PC booter without interrupts. You could pull the keyboard until key data shows up. It's really dumb. because you'd like to actually be doing other things. And you could build a timer by figuring out how fast the processor goes and creating a loop of the appropriate size so that you actually just spin on the processor until a certain amount of time elapses. That sounds great. So we don't have to use interrupts, but really we should. So we set up the interrupt descriptor table register with a new interrupt descriptor table. Remember, previously it was an interrupt vector table, which is useless in protected mode. Re-enable interrupts, and off we go. Okay. Now we can actually start doing kernel-y stuff. Okay, any questions about this process? Yes?
So, protected mode,
which register does it use to determine the base address? So if you're talking about a segment, the base address will be in the segment descriptor that's in the global descriptor table register. What's used to index into that is the value of the segment selector. So for example, CS will be set to some value. And what you'll notice in our operating system is it'll either be, I think either 1 or 3, because those are the indexes into the global descriptor table. You'll actually have 2. One is for user mode and one is for kernel mode. And in that segment selector, the segment selector, I can't remember if it's 8 bytes, it's probably 16 bytes or something like that. But one of the fields in that 16 bytes is, here is the base address, or here's the value to add to whatever addresses the program emits. The CS is the index into that table. Yeah, well, the program can change CS, but if it changes it to something that's not in the global descriptor table, then the processor will generate faults, and the operating system will step in. Yeah, so if it tries to change it to the kernel one, it's allowed to, but what will happen is when it tries to touch that memory, it's still in user mode, and the kernel memory is set up that it's only accessible from kernel mode, and so when it tries to access it, you'll generate a protection fault, and the OS will step in and kill the program. So yeah, it's interesting because you might say, well, the program is still allowed to set it to these other values, but the system is set up so that there's always protections enforced so that if the program tries to do something naughty, it will still generate faults. The operating system will still find out the program's trying to be naughty, and the kernel can kill the program. So you're always protected that way. Does it make sense, everybody? It's kind of really important to understand it because we'll start getting into user mode in a couple of weeks, and you'll start seeing how this all fits together. Okay, any other questions? Yes, exactly right. We do have to change into user mode at some point. We're not going to talk about that today, but that is another thing that happens. If you think about it, the kernel, what I'm going to talk about next is the kernel still has to do some other setup stuff. Not very much, but it has to do some other setup stuff. And then typically what it does is it creates the first process. And the first process is in user mode, and it tends to be an idle process so that if the processor has nothing else to do, it can always go back to the idle process, and that runs in user mode. And so that's how it gets into user mode. So yes, at some point the kernel has to transition into user mode. And that's when you exit the kernel for the very first time. But all this other stuff still happens in kernel mode. Okay, any other questions? These are cool. They're just a little bit ahead of our focus right now. But they're still cool, important questions. Right? All right. Let's see. So yeah, the kernel is ready to take over. Now, of course, we can't use BIOS anymore, which is lame. So what do we do now? Well, this is where we have to start thinking about device drivers. And what you all will be doing on the second project is creating really simple, limited device drivers that have to support one device apiece so that they can interact with the computer hardware. So you want to have some encapsulation around this grossness, because all hardware is gross in some way or another. I suppose there's beautiful hardware to interact with, but a lot of it has little grungy details and nuances that you don't necessarily expect at first. And so you have a device driver that encapsulates that grossness and exposes a very simple, clean interface. Like Linux has character devices and block devices, and block devices encapsulate all the details of actually interacting with the the ATA controller that's on the bus so that it can actually send and receive data to the disk controller. those kind of things. You don't want to do that in your program. You just say, here's a block of data, do stuff with it. Okay, so that's what the device driver does. And so frequently what happens is the devices have already been initialized to a certain point, but they may not be the way the OS wants them to be. And so it can go in, reprobe devices, reconfigure them so that they're the way the OS wants them, and then the device driver can just carry on doing its tasks. So typically you'll see hardware reinitialized at that point. Okay, so that's the general idea. This is what gets us up to the kernel beginning to do kernel-y stuff. Scheduling, virtual memory management, process, address space isolation, all of that kind of stuff. Okay, so these were the details. I just want to throw these up here so you can see the whole mechanism. But you can see how each step has to take a little step forward to expand the capabilities, expand the complexity of what we're able to do, and get us to the next phase. So you can think of these as little steps that get bigger and bigger as we finally get into our operating system. Okay. The other thing that's really interesting to mention is that Windows also has tried to maintain backward compatibility. This is something, if you think about it, Linux has not really tried very hard to do. And, you know, it's a great approach. It certainly means that all your software is going to not suck. But like GCC will not even emit 16-bit real mode code. Like, why? Why should I when I have 32-bit protected mode to use? And that's partly why our PC booter is going to get into protected mode so that we can write the rest of our program in C instead of having to write it in assembly language. Which you may find it funny, but this may be the first time where C was the high-level language in the project you were working on. Normally it'd be like, oh, I'd really love to write this in Python, or I'd really love to write this in Haskell because they have all these really awesome language facilities. I don't have to worry about memory management and all that kind of stuff. But when your low level is assembly language, you can't wait to get into C because it's like, oh, C is so much easier than assembly language for writing code. So anyway, Windows still has to maintain backward compatibility, and so you still have DOS programs that use BIOS calls. Well, what do? It turns out to be pretty straightforward. We just replace the interrupt handlers with our own interrupt handlers that do the things that we need to do. Okay? And so this is what Windows does when it needs to run 16-bit programs that still make BIOS calls. Okay? So that's kind of neat. There's also a special virtual 8086 mode that processors, the IA32 processors have. And if you have a 16-bit DOS program, you can run it in that virtual 8086 mode so that it still looks like a real addressing mode system inside of the 32-bit protected mode. So Windows, not Windows, but IA32 has all these facilities for backward compatibility as well. And Windows leverages those things to enforce all of its operating system guarantees pretty effectively. So that's kind of a clever little technique that they use. Linux doesn't really do anything like this because why? Just run it in an emulator if you really want to run some 16-bit program on Linux. Okay? So that's another interesting little detail here. Okay, so we see that IA32 Bootstrap is hideous. There's not really any other way to describe it. So we have all of this because we want to maintain backward compatibility, even this A20 address line thing, which is just bizarre if you think about it. And of course, once we get into protected mode, we don't have any support for our devices. So we have some issues that we have to deal with. And I've kind of harped on A20. Well, there's a reason. It's even worse than you thought. You have 3 different ways that it can be enabled. And if you think about it, that means you have multiple ways to check if it's already been enabled. So you have an interaction with not any addressing subsystem, but the keyboard controller. Because when they were designing the first PCs, they needed something to run A20 through so that they can enable it and disable it. And, oh, hey, look, the keyboard controller has a spare input and a spare output. Let's use that. So that's why you talk to the keyboard controller when you want to access more memory on these old systems. Seriously. So BIOSes started adding calls to support A20 address line enabling. And of course, the bootloader or the BIOS itself may have already enabled A20. So you have these various things that you have to think about if you want to do that. And of course, that's just A20. All these other hardware facilities have a whole bunch of other little vagaries. Like one of the things I want you to do on the booter is to do some basic interactions with VGA. Okay, well, that's cool. Has anybody here like done like basic VGA? I know this is really basic compared to what you can access now with DirectX and OpenGL and all that kind of stuff. Anybody tinkered with VGA before? So like that's all we had when I was in high school, and that's what we had to program. And so I wrote programs that would talk directly to the VGA card, writing to ports and switch it into different graphics modes, switch it into freakish graphics modes, change the color palette, which is something you could do. When you had programs that would like fade in and fade out, that was like mind-blowing at the time. And the way they would do it is they would put all the data into the video buffer, and then they just changed the color palette. So it would change the mapping from the pixel value to the colors that were sent to the graphics monitor. And so you could manipulate all of that through I/O ports. The only problem is there were standard ports, and then there were special ports for whatever specific VGA hardware you had. So all of those kinds of things also factor into providing device drivers. And that's why you have a device driver for this card, and a device driver for that card, and a device driver for this thing and that thing and the other thing. You have to support all the different ways that people approach things. Standards are really only suggestions a lot of the time, which is too bad. Okay, so people tried to start resolving this issue by introducing new mechanisms available in the system. So we had plug and play, which you may have heard of before. Basically, that was a way of having devices talk to the operating system and tell them, this is the kind of device I am. These are my capabilities. These are my address ranges I would like, and so forth. And so the hardware bus had to actually support it. You didn't see it in the older, there was a bus called ISA, which was just stood for Industry Standard Architecture. It was like, okay, well, that's nice. It's the industry standard. Let's use it. But then there was another one called PCI, Peripheral Component Interconnect, which came along, and the devices on the bus could actually say, hey, this is what I am. So the standard actually was changed to support discoverability. And we still use it's like we're 4 or 5 versions down on PCI now, so it's very advanced now. It used to be like only a 33 megahertz bus. It used to be really slow. I think you could access 16 bits at a time, or maybe 32. Maybe they had taken the first step in the 32-bit, and so that was very exciting. But anyway, so you have all these different buses, and USB is a really good example of a plug-and-play bus as well, where devices are discoverable. If you're curious about playing with this stuff, and you do want to stay within the comforting world of Python, you could look at PyUSB, which actually allows you to query the USB devices that are connected to your system. And you can look at their device IDs. Those are all standardized. You can ask them other questions about what they can do. So it's kind of fun if you want to tinker with that kind of stuff. But all these buses were designed to facilitate discovery of devices on them, so you could find out what they are and how to interact with them. So once you start having plug and play, then the BIOS starts getting more sophisticated in what it provides to the operating system. And so typically you would see BIOS build tables of data that the OS can then look at. And we started in '97 with this thing called the Intel Multiprocessor Specification, which I don't know why, but just for kicks, I threw it into the specs directory so you can look at it. It's kind of fun to read how to actually discover multiple cores or multiple processors on your system. And it builds tables that you could then go in and pull all the details of your processors. And notice important details like what are their APIC IDs. Because if I'm going to send a message to another processor, I have to be able to send an inter-processor interrupt. So you have to know its APIC ID. So you have to get that somewhere. Okay. Multiprocessor spec also specifies multiprocessor bootstrap, which is basically like single processor bootstrap, except that all the other processors instantly run a halt instruction, so they all stop, and then the one booting processor has to set up so that they can start running, and then it sends an interrupt to them all to wake them up, and then they start doing their thing. So you can read about it in the multiprocessor spec if you're curious. Okay, so ACPI is another very widely used standard, Advanced Configuration and Power Interface. And again, it basically has a whole bunch of tables that say, this is what the hardware has. This is what we can do with the hardware. And all of it was accessible through this one entry point. Well, what is the entry point? Well, it's a structure. And the structure starts with a signature. Let me see if I actually say this here. No, I don't. I think I say it on the next slide. So you have to hunt for this root system descriptor pointer because you don't know where the BIOS might stick it. So you have to find it, and then you can start utilizing it. And like I say, the tables include all the details you might need to know about all the major parts of the system. Set up by the firmware, and then the operating system can access it. And this is all based on pluggable devices that are discoverable on buses that support discovery. Okay, so we have to search for it. It could be in the extended BIOS data area. Let's look there. Or it could be somewhere else. Let's look somewhere else. And so you have to kind of hunt for it. And so this is like operating systems that supported ACPI had to go through this process. They had to look for the signature RSD space, PTR space, and then there was other stuff, and then there's a checksum. And what you would have to do is hunt for that sequence, and because I suppose it's possible this signature could occur in some other context, it's hard to imagine, but you had to compute a checksum, and if the checksum computed properly, if I remember correctly, you just add each byte together and see if the final result is 0. If you add them all together, so you have overflows occurring and so forth, but if you end up with a checksum of 0, then you're happy. You know you've found the root system descriptor pointer, and then from that you can follow pointers to all the other tables. Okay, that sounds good, but what if the root system descriptor pointer table doesn't have an entry for something? Well, then you get there and the checksum doesn't add up. So you have to keep computing checksums as you navigate this table. Okay? So it's a little bit frustrating, but I suppose it's way better than having to talk to all these devices yourself. Okay, so this was a big step forward, but it kind of doesn't feel like it. It kind of feels like just a little step forward. All right? This was one thing I was thinking. If you aren't interested in building a game, you could always build a program for your booter that actually goes and finds these things and displays them and allows you to navigate through all of these tables of data. Probably way more boring than it even sounds. So, but it would be another thing that you could consider doing. All right, any questions on ACPI? All right, so you can imagine that operating systems could use this information very well. Now, thankfully, we don't do that anymore. But still, the hardware supports it just in case you're running an operating system that needs it. But what we've started doing is moving to a new mechanism called UEFI. Because the BIOS only helps us a little bit, and only in real mode. It doesn't really help operating systems. So let's get something better. Okay? And so this new standard has emerged. I say recently, it's actually starting to become increasingly distant in the past. So probably in the next few years, I'll take out the recently. But it's becoming more and more widely supported. In fact, I think most hardware now can support UEFI operating systems, and most operating systems can run on top of UEFI. And it basically completely supplants BIOS. BIOS goes away. Why did we need UEFI? Well, there was this processor called the Itanium. Anybody heard of Itanium? A couple of you. Does anybody know what's special about it? No? Sorry, it was I saw. Do I say? Well, yeah, so 64-bit, couldn't run BIOS. But what's special about it? There was something really unusual about it. It was kind of a big step for Intel, and it was a big giant flop. Yay, big risky steps sometimes end up in flops. So it was one of these very large instruction word processors. So you could have instructions that had multiple branches in the same instruction in case you wanted to do branching flow control really efficiently. It was a pretty clever processor, but it turned out to be really difficult to write a compiler for it. And so people were like, okay, this is kind of lame. I'll just get more of these cheaper processors and run them in a big cluster, and we don't really need Itanium. And of course, you know, you have 64-bit on IA32 now, or I should say x86 64, so you don't really need Itanium so much as well. One of the cool things about Itanium is it is a true 64-bit processor, whereas on the Intel IA32 processor family, we really only have 48 bits of address space. This actually had a true 64 bits of address space, so that was one nice thing. But yeah, Itanium couldn't run BIOS, but we still needed to support an operating system. So Intel started thinking of how are we actually going to do this? And so they created a standard called EFI, which then became widely supported and became UEFI. Okay? Unified Extensible Firmware Interface. Now there's actually standards for it. And like I say, it is a firmware interface standard. So we have at the lowest level hardware, as always. And then we have software running in read-only memory called firmware on top of it. And then UEFI says these are the operations that need to be provided, and these are how to provide these operations. And then other things sit on top of UEFI. Okay, so that's where it sits. It doesn't sit necessarily directly on computer hardware. It sits on top of firmware that implements the facilities that UEFI needs to provide. Okay, you'll see why when we start going into UEFI. Okay, any questions? All right. So, yeah, it is modular, which is really neat. UEFI has the ability to install custom pieces of software, and you can remove them as well. But there's a certain set of facilities that are always there so that you can actually rely on it. So you can think of this as being like a mini operating system for the computer. It doesn't allow you to run user applications. It allows you to manage operating systems. So in a sense, it's kind of like a hypervisor, but not quite, because it's really for running one operating system, not a bunch at the same time. So yeah, you can install bootloaders for operating systems. So this is what operating systems that support UEFI will do. They'll install their bootloader into the EFI system so that it can then boot the operating system. It also allows UEFI to take care of multi-boot. So now you don't have to do some weird thing with chaining bootloaders and so forth. All of them go into the UEFI system, and then it can just start whatever operating system you want. Okay, so like I said, you can install UEFI applications, allow various things to be managed. So now we don't need our BIOS setup anymore. Now we can actually have an application installed by the hardware vendor that knows how to manage all of the settings on the computer. So it's kind of neat. You can actually do all of these things through UEFI now. Yeah, and so like it says here, you run in the pre-boot environment, so before the operating system is loaded. That's called the pre-boot environment in the UEFI documentation. And there's various tools that you can use. There's even a command shell. Okay? Has anybody experimented with UEFI stuff? Probably. Is there anything you guys haven't tried? Yeah, probably. What have you done with it? Like,
Linux was a pain to install.
yeah, oh, I know. You know, I actually tried to set up the 32-bit Linux Mint on UEFI virtual machine. And so I got into VirtualBox, and I was trying to, I'm like, click the UEFI button. This should be fine. And I started up, and it's like, here's a shell. Here's a shell in your pre-boot environment. Have fun. And I'm like, screw this, reset. We'll go back to BIOS for now. So you can see that VirtualBox's UEFI support is not really that complete yet, but it's getting there. But anyway, you can provide various kinds of applications that run under UEFI. It provides abstractions for interacting with hardware, which is really nice. So now your OS loaders can expect to talk to whatever storage device you have. Is it SATA? Is it whatever, kind of, device that you might have? UEFI obscures that. You just have simple abstractions that you utilize to load your operating system off the storage device. Or off a network, which is another thing you can do through UEFI. Okay, yeah, so there's a lot of services. I call them UEFI protocols. Well, it's not me. It's actually the standard calls them protocols. And the way to think of these UEFI protocols is in the same way as programming language interfaces. It's a set of operations that you can perform that are standardized, and protocols are the specifications of those interfaces. And so if something implements a particular protocol, you know it has a certain set of operations you can call through. Okay, and so like I say, you're loading images. So I want to pull an image off a disk and display it on the screen. Well, there's protocols for that. I want to do networking. There's protocols for that. So I can say, hey, tell me what network interface controllers there are so that I can start interacting with the internet or something in your pre-boot environment. I want to suck down an image and then decompress it into memory. Well, those are all things that are provided by UEFI protocols. Okay, so there's a ton of support for all kinds of interesting things in the pre-boot environment. Sounds way cooler than BIOS, right? I mean, already I look at this and I'm like, wow, you could build some really neat software for bootstrapping, which, I don't know, I guess it's good that I'm teaching the OS class because that's the kind of thing that turns me on. So, doesn't turn everybody on. So, let's see. So services divided into boot services and runtime services. So boot services are only available before the operating system starts. When the OS starts, the boot services go away. They're taken out of memory. Runtime services are always available. They might be things like suspend the system. I need to go into a power save mode, or I need to hibernate. So now UEFI is actually providing some real facilities to the OS to use. So the OS doesn't have to provide that anymore. Okay? So you have these two different kinds of services, and they have their own protocol specification, so you can write your own runtime services and plug them into operating systems if you wish. So it's a very extensible, I guess that's right in the name. It's a very extensible approach. It's really powerful, and I love it. I think it's a really great idea. Now, UEFI, like it says here, includes several earlier standards, so all your ACPI tables are still available. They're slightly different. We'll talk about how they're slightly different in a second. Also, UEFI is kind of like Java in that it says this is the way things must be in the hardware if you're going to run. And I say it's similar to Java in that Java says how large an int is. Java says how large a char is, and so forth. UEFI says things have to be such and such a way at startup so that the operating system no longer has to jump through all these hoops. UEFI takes care of it, and the OS can just go on to doing OS-y things. Okay, so UEFI has tables in memory, and you might think, oh, okay, that kind of sounds like, rerun of the past. And it kind of is in some ways, but the neat thing about it is it actually stores function pointers in its tables as well as data. This is how the protocols are specified. You know, we all went through in CS24 how classes expose their member functions, and same thing with interfaces. Well, if you just have a table of function pointers, then you can have them point to the implementations of your functions, and you can have a single protocol that can be implemented in many ways so that you can provide varying operations depending on device or protocol or whatever. So this is a really simple hello world. This will become Project 2 in a few years, I'm sure. Okay, so EFI main, this is the entry point to your EFI application, and you get an image handle and a system table, which you have to initialize from the image handle. That's the initialize lib line. And so once it's initialized, all the function pointers have been filled in, all the table pointers have been filled in. One of them is console output. That's what conout is. And then basically you call conout's output string function to output the string hello world. And you'll notice it's a char 16 star because UEFI only does Unicode. You know, I like computers that are usable, or I should say even in Bootstrap, they're able to use languages other than US English. Okay? So that people elsewhere in the world, there's other places in the world it turns out, and they'd like to use computers too. So we'd like to be able to have their own languages for their Bootstrap. And so you can do all of that stuff very easily in UEFI. Okay? We still have rn, /r/n. Again, I don't know if anybody has gotten to this point in the assignment, but when you're on the PC hardware, /r I think just moves down a line, and then /n, or maybe I got it backwards, you'll have to look. No, /r is a carriage return, right? So that goes to the beginning of the line, but doesn't go to the next line, and then /n goes to the new line. So if you want to actually go to the next line, you have to do both of them. If you just want to go to the beginning of the same line, I think it's the /r, but you'd have to check that yourself.
For what it's worth, usually it's /r/n, not /n.
Yes, and so this is the way that it's in the UEFI example, if you look in the UEFI specifications, but I don't know why. You know, you'd have to talk to somebody else. There's actually a really stupid anachronistic reason why we have two characters for this anyway. Does anybody know? I'm sorry? Yeah, teletype is the right answer, yeah. Because sending one character wasn't slow enough for the teletype to return to the next line. And so they said, well, sending two characters is slow enough to get the teletype to go to the next line, so we'll require two characters to go to the next line. I tell you, hardware is just, it is a cruel mistress. So, yeah, this is why we like drivers, because it encapsulates all of that detail. Okay, so another picture. Let's just try to get through the last few things in the last few minutes. Here's another picture of UEFI. You will notice that there's something new here. There's a couple of new things, but there's something new here, which is a can, which usually represents a disk. So you'll notice that disks are actually a very important aspect of UEFI. And this is where when you install UEFI applications, you install UEFI services, If they're not part of what comes prepackaged, then they go onto the EFI system partition. Again, probably many of you have actually seen some kind of EFI system partition, and this is part of the UEFI specification. Okay? And it tends to be something that is simple to support in firmware. So FAT32 is really popular for the EFI system partition because it's really easy to write code to do FAT32. Well, really easy compared to like NTFS or HPFS or something like that. Okay, I don't want to write it, but I mean, one could. Okay, another issue, disk sector addressing. So we had cylinder head sector, which I mentioned briefly. The real constraint here was that we could only access disks up to about 8 gigs with cylinder head sector. And so logical block addressing was introduced that allows us to get up to about 128 petabytes. Okay, if you think this is like unbelievably large, because just wait, it gets even more exciting. So yeah, we can get up to 128 petabytes this way. So that's neat, but the problem was that master boot records still only had 32-bit values for the logical block addressing. So you're still limited to about 2 terabytes, and you may have encountered this, that there's a 2 terabyte limit in some older, I mean, this is a really good reason to switch to GUID partition tables instead of master boot records for your disks, because there's no 2 terabyte size limit. And this is starting to become really serious because I can go buy a box of like what, 6 terabyte disks now and just slap them into a computer, and now I have like a huge thing, and I'll start running into this size limit if I use a master boot record. So the solution was GUID partition tables. What's a GUID? Okay, another term that you're going to run into all the time if you haven't already. It's a globally unique ID. It's actually generated from both the current time and ideally your NIC's MAC address, so that it's actually kind of unique in both time and space. That was the idea behind it. So it's a 128-bit identifier that may actually be unique in the whole world. So that's kind of neat. And so the partition descriptors use 64-bit LBA values, which now gives us, anybody know what a zettabyte is? Yeah, a lot is a good answer. A billion terabytes is also a good answer. A billion terabytes, you know. Good, because I'm almost out of space. So it's a good thing that I can do that.
But it's also true that like people have petabyte data sets.
People do have petabyte data sets, but they typically don't have them on a single disk.
We're getting there.
Yeah, no, we are getting there, no question. But the problem is that I/O performance is still a thing. And so if I have a petabyte database, I probably want it in a bunch of disks I can access concurrently instead of one disk. But yeah, like you say, we're getting there. I'm sure in my lifetime, we'll be like, yeah, can you guys remember the day when we only had zettabytes of space? Because it's like, man, that was so small. And I'll be like, yeah, kids, when I was young, I wrote a program and it was 200 bytes and I was happy. Yeah, right.
It's funny because like playing a bunch of video games, it's really satisfying whenever something comes in and it's like 100 megabytes. And you're like,
Yes.
whoa,
Yeah.
100 megabytes.
Yeah, it's funny how these size things change. All right, let's wrap up really quick. So partition types are GUIDs now, so they're standardized. That's really nice because the MBRs had 1 byte for the partition type. Linux swap would be one value, Linux boot would be another, and they've definitely been reused over the years. So GUIDs are good for partition types. There's a few other details here which I would have loved to cover, but we're out of time, and I don't want to take up your lunchtime. But the one thing I might mention is that GUID partition tables, they put one at each end of the disk. What a good idea. Because it used to be that one sector failing, and I've had this happen right before class, one sector fails and it's the wrong sector and your disk is now useless. So having 2 GUID partition tables, one at each end of the disk, is actually a really good idea. Okay, let's see. A few other details here. We're not going to... Oh, I do want to mention, not everybody supports UEFI in the same way. Apple still sucks in this regard. It does not use the EFI system partition except for firmware updates and other staged installations that require rebooting. So if you want to install EFI Linux on your computer, it's like, good luck. You'll probably jack up your Mac stuff.
Well, that's what Refind is for.
Yes.
It's exactly designed to fuck with Mac in the way that...
Yes. And so I just wanted to throw these things up here because Refind is actually on there. There's a variety of resources if you want to learn more about UEFI. Please don't turn any UEFI booter, or I'll be confused about how to run it. I'll probably be able to just break into Mike's office and use one of his computers. But yeah, there's a lot of information on the internet about UEFI, so you can certainly look at that if you want. Okay, so next time we'll go ahead and start up with processes. We'll start talking about what K-threads are and so forth and how we utilize them. That's next Wednesday because we have no class on Monday, right? Yay, okay, so we'll see you all then.